Okay. So, I'm recording today. I record anyway, as I said earlier, we have a student who is homebound right now, so we record everything. Different hours I record, so they're always online if you miss. Or you just miss me. Then you can listen to me. Wow. You guys are the most depressing group of people I know. All right. So yesterday we were talking about meiosis. What's the point of meiosis? Say what? 6 cells. Sex. No, thank you. To make sex cells. Okay. Why do I need meiosis to make sex cells? Mitosis doesn't work. Why?
Because you would end up with too many chromosomes.
All right. Mitosis would give me too many chromosomes. So what's meiosis do that mitosis doesn't do? Doesn't go through an second S phase, so what? Compared to, so again, in meiosis, we actually reduce the number of chromosomes. We create cells that have haploid numbers, or 23 chromosomes, where mitosis is always going to give you the diploid number, 46, which would create the problem that was just mentioned. If we were always using mitosis, we'd end up doubling the genetic material every generation. And eventually you'd get to a point where you just simply couldn't hold that much genetic information. Yes or no? So meiosis specifically takes place in the testes and the ovaries. It's specifically for reducing genetic information from diploid to haploid in order to keep the number of chromosomes consistent within the species. Yeah? So we were going through the process on the board, and I know we've already gotten through phase 1, but just a quick recap. In meiosis 1,
Teacher, just a notification that Skyward is back online. If you could please update your attendance and re-log in. Skyward is back online. Thank you.
Hallelujah. So if we go back to all right, Skyward's back on, but the smart board is still dumb. Sorry, 1 second here. So if we go back to what we were talking about yesterday, in phase 1, prophase 1 begins the very same way as mitosis. Nuclear membrane dissolves, centrioles splits from 1 to 2, and it starts to form the spindle fibers. Chromosomes DNA starts to wind up and form chromosomes. All that's going on. The difference, though, is near the end of prophase, these homologous pairs of chromosomes begin to group together in groups of 4 called tetrads. This we don't see in mitosis. Right? Just to recap, how many chromosomes would have been in the original parent cell for this cell? Heard 4 and 6. 4. There'd be 1 red one, 1 long blue one, 1 short green one, 1 short black one. That would have been the original cell. Original parent would have been 4 chromosomes. Long red, long blue, short green, short black. Okay? Why are there 8 chromosomes right now? We've already gone through the S phase. We've already made our sister copies. Each chromosome made a sister copy. How many homologs are up here? Two pairs. What are the pairs? Again, homologs are based on the length. Based on the length and what genes they contain. Chromosomes with the same length that carry the same genes are homologous. So in this case, it's intended the red pair and the blue pair are homologs. One would have come from your mother and one would have come from your father. And also, the other homologous pair would be the short black one and the short green one. So there's two homologous pairs, total of 4 chromosomes in the original parent cell. We're currently at 8 chromosomes because we've already gone through the S phase. Big difference is how they line up during metaphase 1. During metaphase 1, they line up on top of each other, not next to each other. The homologs, that is. If this was mitosis, the homologs would all line up independently in pairs. You might have the red long ones, then the short black ones, then the long blue ones, then the short green ones. They'd all be side by side in pairs. That's not what's happening here. Instead, we have the homologs grouped together in a group of 4, one on top of the other. Who's on top, who's on bottom, that's totally random. Could have just as easily been red on top and blue on bottom, or black on top and green on bottom. That's totally random. That's where you start to get some variation. Right. Because of the way they line up, then, during anaphase, when the spindles shorten, we're not pulling the sisters apart, we're pulling the homologs apart. What that is doing, to stress again, is that's giving different information to each end of the cell. One end of the cell is getting the blue gene and the green gene. So let's say the blue is blue skin and the green is green hair. One end is getting a blue skin, green hair combination. The other end is getting a red skin, black hair combination. Yeah. If this was mitosis, I would be getting a blue and a red skin gene, and I'd be getting a green and a black hair gene. I'd be getting all 4 genes. But here I'm only getting one or the other. I'm getting the blue pair or I'm getting the red pair. I'm getting the green pair or I'm getting the black pair. We're beginning to separate the genetic information. Because again, as a parent, you only get to give one of the homologs because your partner is going to give the other. You don't get to give your child both the red skin gene and the blue skin gene. You only get to give it either the red skin or the blue skin. As the parent, you only get to give either the green hair or the black hair. You don't get to give both. Yes, no? So then in telophase, again, fairly normal steps. Nuclear membrane reforms, spindle fibers dissolve, those types of things. This has got 4 chromosomes, but it's not an identical cell. We've not made an identical cell like we would in mitosis. If this was mitosis, each cell would have 1 blue, 1 red, 1 black, 1 green, and they'd be the same. Instead, at the end of the first division, I do have 4 chromosomes, but I only have 2 of each. I only have 2 kinds. I don't have all 4. So in this one cell, because of the way it lined up, I've got a blue-green combination, and in the other cell, I've got a red-black combination. I'm separating out what the genes are going to be. Questions at this point? Don't know what its problem is today. So let's go. I know we got through most of this, but let's just pick back up. So then we start the second division. And we again go through very similar steps. Nuclear membrane dissolves, spindle fibers form, centriole split, all that good stuff. The key is we do not go through, as was mentioned earlier, we do not go through a second S phase. We don't copy the chromosomes again. So in blue here, if it's mitosis, looking over here on the whiteboard, in mitosis, there's 46 chromosomes in the beginning cell. but it goes through the S phase. Everybody's more interested in writing. So over here, there's no second S phase. No second S phase. So normally this cell would be 46, but it goes through the S phase, and 46 becomes 23. 46 goes through the S phase, it becomes 92. It's going to double. And then you split that cell in half, 92 becomes 46 and 46 again. That's what happens in mitosis. In meiosis, again, you started with a cell at 46, but you doubled it to 92. You split the cell into 46, 46, but we don't go through a second S phase. And since we don't go through a second S phase, when you split it a second time, you end up with 4 cells, each with 23. So the lack of that second S phase is critical to cutting the number of chromosomes in half. Duh. Nothing in the world excites you. I can stand here in my underwear and do this, maybe. I could at least get your attention. I don't know. Whoa, what happened? That's true, I would too. All right. Anybody watching this at home, this stupid board is not working. Sorry. Everything smart in here is me. All right. So, had we not gotten to this phase? By the amount of writing, we must not have gotten this far. You guys were the slow group yesterday then. Okay. No, not personally slow. Okay. All right, sorry, I thought we'd already gone through this phase. So when we get to phase 2, we're going to go through prophase, metaphase, anaphase, and telophase again. In this case, we're going to see it's exactly the same as mitosis. It's going to work exactly the same as mitosis. So nuclear membrane dissolves, centrioles split into 2, spindle fibers are assembled, the DNA wraps up and becomes visible, but as I just tried to stress, there's no second S phase. There's no second S phase because you already got a second sister copy. There's nothing left to copy. Mm-hmm. So then when we move on, So when we move on to metaphase 2, it's going to look just like mitosis. The chromosomes are now lined up along the equatorial plane in their pairs. Notice we're not stacked, they're in 2s. Their sisters are lined up across the equatorial plane. The spindle fibers will attach to the centromeres just like before. So in the one cell, you got the blue chromosome and the green chromosome lined up side by side, not on top of each other. They're not homologs. And in the second cell, you got red and black lined up side by side, just like in mitosis. Then in anaphase, it's the same idea. Spindle fibers are going to shorten, and we're going to pull the sisters apart. Right? Just like in mitosis, the centromere is going to be split. The 2 sisters are going to be separated. So in this case, the first cell, one long blue gene is going to one end. The other long blue chromosome is going to the opposite end. One short green is going up, one short green is going down. Same thing is happening with the red-black combination in the second cell. So just like in mitosis, we are separating the sister chromatids. So metaphase 2, anaphase 2, identical to what happens in mitosis. I'm going to hold a moment to give people a chance to catch up. So by the time I get to telophase, the cells are going to go through the typical steps again. We're going to reform the nucleus. Spindle fibers are going to dissolve. The cell's going to go through cytokinesis and split again into not 2 cells, but now 4 cells. So as I look at telophase, in each picture, the nucleus is reforming. In this particular cell, you're going to end up with 1 long blue chromosome and 1 short green chromosome. And in this particular cell, you're going to end up with cells that have 1 long red chromosome and 1 short black chromosome. Each cell now contains how many chromosomes in the picture? 2. Our original cell had how many? 4. So we've gone from cells of 4 chromosomes down to cells of 2 chromosomes. We've gone from diploid to haploid. Notice each cell contains 1 of each homologue. So if you're the 2 cells on the left, let's say those are 4 sperm cells. If you're the 2 cells on the left, if either one of those would fertilize the egg, Dad is contributing a blue gene and a green gene. Again, if we stick to the analogy I was using earlier, Dad would contribute blue skin and green hair. Now, Mom gets a 50% say in that. But if those were the sperm, Dad would contribute blue skin and green hair. If it was one of the sperm on the right, Dad would contribute red skin and black hair. If the chromosomes had lined up different, he could have made a red skin, green hair combination. He could have made a blue skin, black hair combination if they had lined up differently. It's totally by chance which way they lined up. But notice we've cut the number in half, and we've got 1 of each homologue. We've got 1 chromosome from the long homologue, and we've got 1 chromosome from the short homologue, because each one would contain different genes. Making some sense. I'm always confident when we have 3 people they get it. It's okay if you don't, but ask questions. Groups. You guys are always so quiet. The second two. These two. They should all be 4 separate cells. They're not really connected. It was just the way the drawing came out. So they're 4 separate, totally separate cells. You can think of them as 4 sperm cells. Each one would be different. Each would be independent. Yes? So you can see we cut the number in half. Notice we don't have a cell with a blue-red combination because then you would have 2 of the same homolog. You'd be missing a hair color gene. You'd have 2 skin color genes. We don't want that. You got to have 1 of each gene. 1 of each gene. Right? So this is how you create your set of 23. And this is how your partner creates their set of 23. So that when you both merge your gametes, you create a new person with 46. 2 sets of 23. Questions at this point? Either the end of today or certainly tomorrow, we're going to give you some practice with this. That's when we'll really start to see who's got it and who's having a little bit of trouble. We got several options. I'm not sure which way we're going to go. Several different options. Okay. I doubt we'll go with the Play-Doh again since you've already done it once. Okay, then let's go forward. This process is different in guys and girls. It's a little bit different. And the primary reason it's different, well, why do you think it might be different between guys and girls? You have different sex organs, good observation. Different functions. What's the function that the female has that the male doesn't have? No. Menstruation is a part of the process. What's the female got to do that the male doesn't have to do? The big difference is the female carries the offspring. That's what really drives the difference. The fact the female has to carry the baby, the male doesn't. That totally changes the strategy. All right? All right? Totally changes the strategy. And we got into a whole long talk of seahorses first hour. But since males don't have any responsibility for carrying the child, for them it's a quantity game. As many as you can. A few of them are bad. Oh, well, no big deal. And really their strategy is, I'm going to make so much, something's got to work. Really is the approach. Okay? The female can't use that strategy. Right? The guy's going to produce, on average, a couple 100 million sperm a day. The female doesn't want to produce a couple 100 million eggs a day because she can't carry a couple 100 million offspring at one time. Wouldn't make any sense. Instead, the female has to focus on creating 1 usable egg per cycle in the attempt to become pregnant. Once in a while, you'll get a female who releases more than 1 egg, and you can get twins or triplets, etc. But that's not the norm. The norm is the cycle is designed to carry 1 child in that period of time. So for females, there's a lot more focus on quality. Males, there's a lot more focus on quantity. Okay? So for guys, well, this is not going to work again, I'm sure. Let me bring up the next page. So for guys, the process is called technically spermatogenesis. Spermatogenesis is the genesis or generation of sperm. It's meiosis is what's being used. And for every single cell in the testes, we will usually produce 4 usable sperm. So for every one cell that you go through meiosis in the testes, you produce usually 4 usable sperm. Spermatogenesis. For males, this begins at puberty, and then pretty much takes place throughout the rest of their life. There really is no stopping of sperm production until death. Now, sperm production will certainly probably fall off as you get into your 70s, 80s, and 90s, but you do still produce sperm. Technically, an 80-year-old guy could still father a child, provided everything is functioning. Right? They still technically could. Okay. And again, since the guy doesn't have to carry the child, really not a big deal. It's made daily. Sperm has about a lifespan, a shelf life of about 48 to 72 hours. If the sperm is not used in about a 48 to 72 hour period, it will be broken down and reabsorbed and replaced with new sperm. After about 72 hours, the sperm tend to go a little bit defective. So you don't want sperm sitting around for months or years before you use it. It's not viable. So if it's not used within about a 72 hour period, it's broken down and reabsorbed and replaced. And so the male is constantly replacing the sperm supply, never quite knowing exactly when it's going to be needed. The male always keeps it ready, I guess you would say. Yes? The sperm that's donated? Well, you have to have a certain media, a certain solution in which you keep the sperm, and you can keep it, again, you can only keep it alive, viable alive for a short period of time, or you have to freeze it. Right? And the freezing process, again, is not a regular freezer. You have to use a liquid nitrogen type process to freeze it, and then make it viable again. The guys will produce it throughout their life. Really, in the average sexual act, sexual intercourse, whatever word you want to use, the male deposits about 400 million sperm into the female's body. 400 million. Of that, we're hoping 50 will actually get to the egg. We're lucky if 50 get to the egg. Okay? It's one giant obstacle course that is not in the favor of the sperm. So, I mean, as far as the female's body is concerned, that sperm is a foreign invader. It's something that her system will attack. So, first of all, the vaginal region is very acidic. So right away, half the sperm die within the first few seconds of being deposited. Then the sperm have to swim upstream against gravity. And they have to get up through the cervix into the uterus. Once they get into the uterus, then it's a 50-50 shot which fallopian tube has the egg in it. Half the sperm are going to statistically go up the wrong tube where there is no egg. So there's lots of things that happen to the sperm that they never find the egg. If we can get about 50 sperm to the egg, then we only takes one to actually fertilize the egg, ultimately. All right, so it's a numbers game. It's a numbers game. It may seem like, geez, how does anybody ever get pregnant? But obviously people do. And so, guys, again, the strategy is I'm going to make so much, somebody's got to make it. And that's sort of the approach that the male takes. Yes? If they're just paternal twins, non-identical twins, yes. Happens to be that the female released 2 eggs during that cycle. Identical twins, it's 1 sperm, 1 egg, and the egg in the early divisions, when you're making those embryonic stem cells, actually splits too far, and you get 2 components that grow, and then both pieces grow into children. They have then the exact same genes. Yes?
So what if like 3 sperm have the egg at the same time?
They won't be able to penetrate. As soon as that first sperm goes through, there is a rapid chemical change in what's called the fertilization membrane, which blocks any other sperm from being able to penetrate. If by some chance more than 1 sperm did, it's not going to develop too many chromosomes. It would not implant. It would not take. In fact, even of successful fertilizations, it's estimated 75% of all fertilized eggs never implant. The body rejects them for various reasons. Twins can either be the females ovulate and release 2 eggs at once. Right? So sometimes both ovaries produce an egg, and if both eggs get fertilized, you get twins. Or sometimes the egg splits into 2 parts. Okay. All right. Girls, different story, because they have to carry the child. So females, they go through a process called oogenesis. Okay. It comes from the word ovum. Ovum is the Latin word for egg. Right. So that's where they get the oogenesis. Okay. Oogenesis ends up with an unequal division. And what happens is, in the female, she produces 1 usable egg. And the other 3 cells become what we call polar bodies. We still quite haven't figured out if the polar bodies have any purpose. We think possibly they play a role early on when the egg is first moving down the fallopian tube. But if they do, they disappear quickly. They end up dissolving and breaking down fairly early in the process. The reason the female has to make 1 large egg is she not only has to give you 23 chromosomes, it's mom's job to give you all your cytoplasm and all your organelles. All the sperm contains is 23 chromosomes. Dad gives you no cytoplasm. Dad gives you none of the organelles. So mom gives you all your organelles. Mom gives you all your cytoplasm plus 23 chromosomes. So in the process of meiosis in the female, she focuses all the cytoplasm and organelles into 1 cell. The other 3 are sacrificed. And again, we're not sure if they have any significant role or not. And therefore, in the human female, on average, about every 28 days, she will produce 1 viable, usable egg. So you are literally more your mother than your father. All of your cytoplasm and organelles originated from your mother. Okay? Including your mitochondria, which has its own DNA. We call this mitochondrial DNA. So all of your mitochondrial DNA comes from your mother. And you can do some interesting tracings of family history through mitochondrial DNA because it all goes through the mother's line. For guys, one of the traits that we think moves through mitochondrial DNA is baldness. And so oftentimes, not 100%, but oftentimes if you look at your mother's father, your grandfather on your mother's side, if they are bald, that is probably your future as well. If your grandfather on your mother's side has got a full head of hair, you're less likely to probably have the issue of being bald. Okay? That's just one example of a mitochondrial trait. Right? So for females, this all actually starts before birth. Female actually starts meiosis before birth. You actually have produced all of your eggs before you were born. Every egg you ever are going to produce has already been started. It's not finished, but it's already been started. And you are born with ovaries that have these immature eggs in them. Then at puberty, when the menstrual cycles begin, then you take approximately 1 egg every 28 days and let it complete maturation. And that egg is then released and viable for pregnancy. Eggs, like sperm, have a very short lifespan. You got about 48 hours to 72 hours for that egg to be viable. If that egg is not fertilized in about 48 to 72 hours, then it's going to break down and disintegrate. So really, there's about a 2 to 3 day window in which you can actually get pregnant. And that's that period in which the egg has been released and is viable for about 48 hours. For females, another key difference is it does stop. There's a period in the female cycle called menopause, which takes place late 40s, 50s on average, where the female will no longer produce eggs, which if you think about it, it makes some sense. Because if you're 70, 80 years old, your body really no longer is equipped to carry a child. So it wouldn't make much sense for you to be still producing eggs at 80 years old and getting pregnant at 80 years old, because that would probably be way too much stress on the body, more so than probably the typical 80-year-old could manage. So it makes some sense that for females, we stop producing gametes at late 40s, early 50s, because our bodies really are no longer equipped to efficiently carry a child. For guys, since they don't carry the child, there's no need to stop. they continue to produce. Right? And so those are some of the critical differences we see between males and females. Oh my gosh. Sorry, I don't know what is going on with this thing today. Worked fine first hour. Give me half a second. So this is just documenting what I've already said. There's nothing I didn't mention there, I don't believe. So this is the guys. So this is just one aspect of many where guys and girls are very different. Not one better than the other, just different. And then in the red is just documenting what I basically said about female. I hit everything there. And again, all that really is driven by the idea that the female carries the child and the male doesn't. Because the female has the extra responsibility of carrying the child, her process is quite a bit more complex, a little bit more involved. Since biologically speaking, the guy is basically a sperm donor, there's not much responsibility or requirement of him. Questions? And let's try that again. Last thing for today, as far as the notes, take a look at the bottom of the page here, where we do a brief comparison of mitosis, meiosis. Similar processes, but some key differences. So the purposes are different, as we've mentioned already. In humans, mitosis is used for growth, repair, and replacement. It's the most common form of cell division we use. And again, meiosis has single one purpose. Produce sperm if you're a male, produce the egg if you're a female. Where does it take place? In mitosis, it takes place in all of our body cells, which is pretty much 99% of our body. And meiosis is exclusively only in the sex cells. If you're a male, the testes. If you're a female, the ovaries. Number of cell divisions, as we can see on the whiteboard next to it. Again, mitosis only divides once. Meiosis, the key is it divides twice, but only copies once. By dividing twice, but only copying once, you can cut the number of chromosomes in half. Therefore, because there's only one division in mitosis, we make 2 new cells. And because there are 2 divisions in meiosis, we make 4 new cells. Again, in males, all 4 cells are typically usable, make viable sperm. In females, only one of those 4 cells will actually end up being used because she has to contribute all the cytoplasm and organelles. Number of chromosomes, again, mitosis is all about making exact duplicates of the body cells, so we produce cells that have 46. And again, the whole point of meiosis is to cut that number in half, what we call the haploid number, so that when sperm and egg meet, we get back to the normal 46, which is important to the species. Anything? Once, twice, sold. Okay. I'm going to step away from the notes then and go to something else here.